Okay, this is just going to be a second example of a buffer problem. Um, just worked out same general method, but we've got something different on the shelf to make our buffer this time. So it's just going to work out a little bit differently. So in this example, we want to make 375 mLs of a 0.050 molar glycine buffer. So in case you don't know yet, glycine is an amino acid, but it can also serve as a buffering molecule. And the buffer we want to make is pH 9.80. And glycine has two acidic protons. So we have two protons that we can lose. The first one has a pKa value of 2.34. That's the easiest one to donate. The second one, the second proton that will be donated, has a pKa value of 9.6. So let's take a look at the structure of glycine and write out the equilibrium structures that we have. So at the most acidic pH that we could get, where all the protons are still on glycine, it would have a chemical structure that looks like this. And the first pKa value, pKa1, which we said was 2.34, once the pH has passed that pKa value, we will lose our first proton, and that happens to be the pKa value for losing the proton off of this carboxylic acid. So once we pass, so when I say pass, think about your titration curves. Once the pH is greater than 2.34, we've started losing most of the protons on that carboxylic acid. And our structure now looks like this, where we have a carboxylate instead. And then it'll be time to lose the second acidic proton. So as the pH, if the pH were to continue to increase, I'm kind of running out of room on this little teeny iPad. As the pH passed the second pKa value of 9.6, we would now lose our second acidic proton, which is one of these on the amino group. So that's at pKa2. And if we drew that structure, we would now have a molecule that looks like this. So I'm just going to call these three molecules A, B, and C. And I will tell you that on the shelf in our lab, when we're going to make this buffer, that we have solid glycine hydrochloride, which means we have the most acidic form of glycine that you can have, and that's all we have. So on the shelf, all we have is a bottle of molecule A. So we know, though, to make a buffer, you have to have a weak acid and its conjugate base. So not only do we need to first decide which two of these molecules of A, B, and C are the weak acid and conjugate base that are in equilibrium in our buffer, we then have to figure out how we're going to get those two molecules, starting only with molecule A. Okay, so first of all, let's just figure out how much of the weak acid and conjugate base, so I'm just going to represent them even though we're talking about glycine. Well, I guess I'm writing in gold now. So how much HA, weak acid, and conjugate base do we have in our buffer? And first, before we do that, we've really got to figure out which molecules is it, A, B, and C. And the way we think about that is we say, okay, we said we had molecule A, molecule B, and molecule C. So pKa1 governed the weak acid A and its conjugate base B, and pKa2 governed weak acid B and its conjugate base C. So the best buffer that we can make has a pH within 1 pH unit of the pKa of that particular buffer molecule. So if we're trying to make a buffer at pH 9.8, then that means we want to have B be our conjugate base and C be our weak acid, because the pKa for losing that second proton was 9.60. So in our buffer, B is going to be HA, and molecule C is going to be our A minus. I guess I should write that as A minus to be consistent. So let's figure out then how much of HA and A minus that we have. So we know that pH is equal to pKa plus the log, the concentration of conjugate base over weak acid. That's our Henderson-Hasselbalch equation. And we know that the pH is equal to 9.80 and the pKa is equal to 9.60. So if we do some math there, like we did in the last lecture video, we find out then that the concentration of A minus is equal to 1.58 times the concentration of our weak acid. So there's our first equation with two unknowns. So now we need our second equation. So to figure out the second equation, we consider how much of our buffer molecules we have in solution. And I think it's easier to work in moles rather than molarity because I like to think of how many of each molecule are floating around in the beaker. How many weak acid molecules and how many conjugate base molecules. So I know that if we have 375 milliliters, there are 1,000 milliliters in 1 liter. And the total concentration on my buffer that we're trying to make, we said was going to be 0.050 moles of buffer per liter. So that moles of buffer will be the total moles of conjugate base and weak acid. So 0.01875, that's what this equals, moles. So that will be the moles of conjugate base plus the moles of weak acid. So that's going to be our second equation, because since the weak acid and the conjugate base are in the same volume, and they're in the same beaker, we can just treat this as moles of A minus and this as moles of HA, because we could just divide out by whatever volume that they're in. So now we've got two equations and two unknowns, so I'm going to substitute equation 1 here into equation 2. If I do that, I get 0.01875 is equal to 1.58 times HA plus the moles of HA. So now I can solve this for moles of HA. If I do that, I get moles of HA is equal to 7.27 times 10 to the minus 3. I can plug back into my original equations to get the moles then of A minus, and that's going to be 11.48 times 10 to the minus 3. So these are how many moles of weak acid and conjugate base I have in my final buffer. So remember, this is molecule B, this is molecule C, but what I have on the shelf is molecule A, the glycine hydrochloride. So all of these moles up here that we have in the final buffer have to be made from my original molecule. So let's first figure out, to get that total number of moles, which was 0.01875, that's how many total buffer molecules there were, moles of buffer molecules. To get that many moles of the glycine hydrochloride, I need to multiply that by its molar mass, which I read off the bottle to be 111.5 grams per mole. And if you do that, you get out that you need to weigh 2.09 grams of the glycine HCl. So that is all molecule A. So the first step then that I need to do once I put that in my beaker is I need to convert all of those molecules, convert all of the glycine hydrochloride into molecule B. So I need to deprotonate all of those molecules. So that means if I started with this many moles of glycine hydrochloride, I need to add that many moles of sodium hydroxide. So I need to add 18.75 times 10 to the minus 3 moles of sodium hydroxide. So if we just assume that I have a 1 molar solution of sodium hydroxide sitting on the bench, because we've always got buckets of base and acid sitting around for pH purposes, then that means I need to add 18.75 mils of a 1 molar NaOH stock solution. So when I do that, all the moles of glycine hydrochloride, their first proton will get deprotonated, and that will turn it all into molecule B. But now I need to turn some of the molecules, some of the B molecules, into the C molecule so that I have the right ratio of B to C to give me the actual pH that I want. So I know then that since I need 11.48 times 10 to the minus 3 moles of molecule C, then I need to add another 11.48 times 10 to the minus 3, or I should just say, to make it easier, instead of times 10 to the minus 3, I need to add another 11.48 milliliters of 1 molar NaOH, because that will convert 11.48 times 10 to the minus 3 moles of B into 11.48 times 10 to the minus 3 moles of C, which is what I needed to have in my final buffer. So to make this buffer, then I would weigh out the 2.09 grams of the glycine hydrochloride. Then I would add 30.23 mils of 1 molar NaOH, so that will deprotonate all the A molecules, all the glycine hydrochloride, into molecule that we called molecule B, and then it will deprotonate the remaining amount and turn them into the conjugate base C so that we're left with the right ratio of B to C molecules. So then I would add some water and pH it and make sure it was correct and adjust the pH accordingly. And then I would finish diluting to the final volume of 375 mils. So this is a case where we had to actually generate the weak acid and the conjugate base in the beaker, starting with another molecule. So it's the same math, but a different way to really think about what the molecules are floating around in your buffer.